Good morning, everyone. My name is Haya, and I'm a research associate in the Department of Civil Engineering in the American University of Sharjah. I'm working under the supervision of Professors Rami and Jamal Abdullah, who are also co-authors of the study. The title of the study is Comparison Between Design Guidelines in Predicting FRP Contribution to Shear Capacity of Strengthened RC or Reinforced Concrete Beams. This is the outline of our study. I'll start with a brief introduction, moving on to the research significance and objectives. Then I'll present the design models we use and the experimental data. Then we'll be discussing the results. And finally, I will conclude with the conclusion. Well, recently there has been high demand in the construction industry to retrofit existing reinforced concrete structures. This is due to the several factors such as neglect and overuse of the structures, increased loading, which could be a result of changing the purpose of the structure, corrosion of steel inside the concrete, and mainly these factors resulted in the accelerated deterioration of the reinforced concrete structures. One of the effective methods used in the retrofitting industry is conducted via externally bonding fiber-reinforced polymers, which are FRPs, to the concrete surface to enhance the shear capacity, flexural capacity of reinforced concrete beams, and the confinement capacity of columns. The main advantages of these FRPs include they have high strength-to-weight ratios, they are non-corrosive unlike steel, and therefore they're durable, they're easy to install, and they're versatile. They can be used in many structural strengthening applications. So our study mainly focuses on shear strengthening for RC beams. As you can see here, there are three ways in which the FRP can be bonded to the concrete surface to enhance its shear capacity. The first one is the fully wrapped scheme, which is the most effective one. However, this cannot be used in many cases where the beams are connected to the slab. This takes us to the second wrapping scheme, which is the U-wrap. The U-wraps are the most commonly used FRP configurations for shear strengthening, and studies have shown that anchoring the U-wraps could enhance the shear capacity similar to that of the complete wraps. The third one is the two-sided or the side-bonded scheme, and this one gives the least enhancement in the shear capacity, and it's the least effective. Therefore, it has been ruled out by many codes such as the FIB Bulletin 90, and as a result, we did not include the two-sided wrapping scheme in our study. The FRPs can be bonded either as perpendicular strips with specific width and spacing. They could be continuous without any spacing, or inclined strips. While typical failure modes of shear strengthened applications include FRP debonding for the U-wrap laminates and a loss of aggregate interlock, or FRP rupture, which is more favorable, of course, for the completely wrapped members. The most failure modes usually occur at strains which are lower than the ultimate strains of the FRP. Therefore, most design guidelines limit the strain in the FRP to a fraction of the ultimate strain, and this is known as the effective strain. Well, the research significance of our project, the behavior of RC beams strengthened in shear is complex. This is because of the interaction between the three components that resist the shear force, which are the concrete, steel, and FRP. And as a result, less research has been undertaken for FRP shear strengthening than flexural strengthening, for example. The accuracy of these models that calculate the FRP contribution to shear capacity is dependent on many factors, such as, but not limited to, the wrapping scheme, the wrapping angle, shear crack angle, concrete compressive strength, number of FRP layers, and FRP time. Many guidelines and standards were developed to predict the contribution of FRP to shear capacity. However, some could be conservative and some could provide unsafe predictions. Therefore, the objective of our research is to compare and evaluate the accuracy of the commonly available FRP shear design guidelines. The design guidelines that are considered in the study are the American Concrete Institute, which is the ACI 440, the Canadian Standards Association, CSAS 806, the Technical Report Task Group, FIB Bulletin 90, and the Concrete Society in the UK, TR 55. The accuracy of the design models was assessed against an experimental database collected from the literature. So here are the design model equations used in this study. As you can see, the models are mainly dependent on the geometry of the section, on the mechanical properties of the FRP, and on the wrapping scheme. And you can also see that the effective strain in the anchored and complete wraps is limited in all the design guidelines to a value which is a percentage or a fraction of the ultimate strain. And for simplicity, we use the shear crack angle as 45, which is conservative, and to allow comparison between the models that does not count for the shear crack angle with those with the variable shear crack angle. Also, we use the reduction factor, or we set all the reduction factors to unity to allow for true comparison between the experimental and the predicted results. So in total, 7 research studies were used overall. We divided the data into 3 parts: U-wraps, complete wraps, and anchored U-wraps. As you can see here in the table, different section details were used with different concrete compressive strength, different FRP types with different mechanical properties, and different wrapping geometry and fiber angle. So this is the table for the completely wrapped configuration. And finally, for the anchored U-wrapped configuration. Moving on to the results and discussion, we plotted the FRP contribution to shear capacity, the VF experimental versus the predicted values for all the codes, the ACI, CSA, FIB, and TR55. As you can see, the points that lie below the unity line, they indicate that the predicted values were more than the experimental, and therefore resulting in unsafe and overestimated predictions. And the points that on top of the line indicate that the experimental values were more than the predicted ones, and therefore these points are considered safe and conservative. It can be seen from the figures that there is a relatively good correlation between the experimental and the predicted values. Of course, some codes are being more accurate than the others. In general, it can be seen that all the codes provide unsafe predictions for the U-wraps, as mainly the points lie below the unity line, and more conservative estimates for the complete wraps and for the anchored ones. This could be because of the strain limit imposed for the anchored and completely wrapped specimens. And while experimentally these wrapping schemes, they provide very high shear enhancement and could result in rupturing the laminates. So moving on. So these are the statistical measures that we calculated: the average of VF experimental over predicted, standard deviation, the coefficient of variance, the mean of absolute error, and the root mean squared error. So these are the tables that show the values for each wrapping scheme, plus a table at the bottom that shows the values using all experimental and predicted data for all configurations. It is clearly indicated that all codes overestimate the capacity of the U-wrapped specimens, with the average VF experimental to VF predicted less than 1, therefore providing unsafe results. The least error was provided by FIB bulletin 90 predictions, and the highest error and coefficient of variation was given by the ACI predictions. As for the complete wraps, all codes tend to underestimate the capacity of the completely wrapped specimens. As I mentioned earlier, this could be because of the effective strain limitations. For complete wraps, the least error was depicted by the Canadian and FIB Bulletin 90 code, while TR55 provided the most conservative results, however, the highest error values. This could be because of the limitations of the TR55 code, which imposes 3 limits of the maximum effective strain allowed in the completely wrapped members. This limit in many cases could be less than the 0.004 limit of the ACI, for example. Moving on to the anchored laminates, all codes except for FIB Bulletin 90 are conservative and they give safe predictions, with all the ratios of the experimental to be predictive to be greater than 1. The CSA gave the best predictions in terms of having the lowest mean absolute error and root mean square error. Although FIB 90 has the least standard deviation values for the anchored U-wraps, its predictions are unsafe with a ratio of the experimental to predicted to be 0.85. This could be because FIB allows the design stress in the anchored laminates to be maximum of 90% limit which we used in the study of the complete wraps. However, in the code, they mentioned that this limit should be determined through testing approval of the anchorage system. Maybe if a lower value was used of, like, for example, 80%, then the predicted results could be more conservative. Overall, the ACIs in the TR55 gave conservative results. However, the lowest error values and the FIB bulletin 90 had the lowest standard deviation, coefficient of variation, MAE and RMSE between all the codes. Still, it is unsafe to use for the URAPs and the anchored URAPs. In general, the CSA provides the safest results and its design guidelines could be safely implemented to design anchored and completely wrapped specimens. So in conclusion, the accuracy of 4 design guidelines, the ACI, CSA, FIB Bulletin 90, and TR55, were evaluated and assessed with the help of an experimental database, and the following conclusions were drawn. All codes provided an average unsafe predictions for the URAP configuration. In addition, all codes underestimated the capacity of the completely wrapped configuration, with the TR55 being the most conservative and FIB 90 the least. FIB Bulletin 90 overestimated the capacity of anchored URAP specimens on average, whereas more accurate results were provided by the CSA code. Overall, CSA gave underestimated results, and its guidelines could be safely used to design anchored and completely wrapped specimens. The ACI and TR55 provided the most conservative results overall for complete wraps and anchored URAPs. These are the references that we used. And thank you for listening. If you have any questions, please feel free to ask.